Welcome to Max and Men's Applied. We're going to be looking at this question here. An open box is to be made from a square piece of aluminum 3 centimeters on a side by cutting squares from each corner and then folding up the sides. Determine the dimensions of the box that will have the largest volume. So let's break that question down a little bit. Basically what it's telling us is we've got this flat piece of aluminum that is 3 centimeters by 3 centimeters, and we're going to cut out the corners in perfect squares and then fold it up, and it's looking for the largest volume. So the big question is, well, what's the dimension of the squares that we're going to cut from this piece of aluminum? So we know the area is equal to the x times y, and in this case it's a square, so those two values are the same, and that volume is equal to x times y times the height. So we're really looking for the x and the y that are going to end up being the inside or the bottom of the box. That'll give us our dimensions of basically the base plate of the box. And we can see when we cut out the corners and then that gets folded up, that piece of aluminum gets folded into a box shape, the actual cutout dimensions of the corners gives us our height dimension. So we can simplify this a little bit because we know that the question is telling us that everything's square. So we know that the x and y coordinates are the same. So the area is going to be equal to x times x, or x squared. And now the volume, instead of being x times y times height, it's now x squared times height. So that simplifies that just a little bit. So now we know what the x's are. Can we get the x's in terms of h using our original dimensions? And so we know that the area is x times x, or x squared. So if we solve for x, we know that the total distance was 3 centimeters. So if we cut out the height on each corner, we end up with, you can see that we end up with 2 h's. So whatever our x is going to be, it's going to be 3 centimeters minus 2h. And so now that we've got the x's in terms of h, can we also get the volume in terms of h? So instead of being x squared times h, now we've got 3 centimeters minus 2h, that term squared times h. So we've basically got our volume in terms of whatever the height of the box is going to end up being, and in terms of our original dimension. So if we do some algebra here and we distribute that out or factor that out and then multiply the h through, we get a volume equal to 9h minus 12h squared plus 4h cubed. So now we can plot the function of volume into Desmos, and we can see what that curve is going to look like. And then if we think of it in terms of h, it makes sense that if the height is 0, you cut out 0, basically the box would be flat, right? So it's not going to hold any volume. At the other point where we've got the 1.5, you can see the function coming down and touching the x-axis at 0. The 1.5, that makes sense also because if we cut out 1.5, our total dimension was 3. So we're basically like just folding it in half. So there's no volume there also. Okay, and we know we can't cut more than 1.5 out of each side, so that other part where it starts to go back up, that's beyond the scope of our original dimensions. So that's going to be, we're not using any part of that curve. So when we look back here, we can see, well, graphically, it looks like at 0.5, a height of 0.5 gives us our maximum volume of 2. So we've basically done the graphical analysis of this question. But the next question is, can we solve the same thing using calculus? So we've got our equation in terms of volume and height. And notice on our graph that you can see we've got 2 points on this graph where the slope equals 0. Appears to be around the 0.5, height equals 0.5, and also 1.5. And so that's what we're going to do with our max and our mins. We can set this now to take the derivative, which we know that if we've got dv dh, right, and the slope is 0, that's at one of those peaks. We're at a peak in the equation. So if we take the derivative of our volume formula, we get dv dh 9 minus 24h plus 12h squared. So now we know that the slope at the max should be 0. So if we set the equation equal to 0, so the slope's equal to 0, and then solve for h, because we've got an h squared and an h, we now need to just put that into the quadratic equation and solve for it that way. And using my quadratic equation solver in my TI-89, I get the numbers 0.5 centimeters and 1.5 centimeters, which is exactly represented on our graph. So this just tells us that that 0.5 is actually the true max, and the 1.5, now you can see that that's the true min. So for us, for our box, we want the maximum, so we're going to use that 0.5 centimeters as the height. So here I'm using Fusion 360 to kind of demonstrate the box, and we've got the height set at 0.5 centimeters. We know the area, the base of the box, should be x times y, and because we took off a 0.5 centimeters on each side, we end up with a 2 centimeters by 2 centimeters for the base, and then we know our height is 0.5 centimeters, and that does in fact give us a volume of 2 centimeters cubed.